So we'll be starting the series off with limits, and the idea of a limit is very fundamental to calculus and all of maths in general. Essentially, there are times in functions where you don't actually have a value, but the neighboring values are approximately closing in at a specific point. So essentially, what a limit means is that it is approaching a specific value, but it is not equal to that specific value. But we can make that assumption that it is equal to that value because of the distance between the neighboring value and the actual value being very close. I'll give you an example to make this thing easier. Imagine sine of x divided by x. So this is what the graph will look like, right? This is essentially just the graph of sine of x and that is multiplied with 1 by x. And this is what it looks like. But now, if I were to do a mathematical just calculation at x equal to 0, sine of 0 is equal to 0. And when x is equal to 0, that basically means that it's 0. So what we're going to get is 0 divided by 0, which is an indeterminate form. It is not a defined form. Right? If you have anything like 5 divided by 5, that is equal to 1. That is a definite form that has a value. But this is indeterminate and it does not have a form. 0 by 0 is therefore an undefined value. So essentially, what I'm saying is that as the value approaches 0 from left and right, um, it approaches 0. It's never equal to 0. So as it approaches 0, you'll get the value 1. Because if I were to do something like sine of 0.00001 divided by 0.0001, you'll get 1. And sine of negative 0.0001 divided by negative 0.001, you'll get 1 again. So it's basically you're making an assumption that as x approaches 0 from the right hand side and as x approaches 0 from the left hand side, it's going to close into a specific value, which is in this case equal to 1. But sine of x by x is never equal to 1. So essentially, there should be, to make this graph accurate, a blank circle over here, which basically means that it is never equal to that value. It is approaching that value. So how do I write a limit approaching from the left and from the right? So essentially, we write lim to basically imply limit. And then we write a variable, which in this case is going to be x. And let's say that it is approaching 0. Then on the other side, on the right hand side, we write the function, which is in this case sine of x. Now, this is the general format. But if it is approaching from the right hand side and from the left hand side specifically, you have to write something else. You have to write a plus or a minus. Now, an easy way to remember this is if it's approaching from the left hand side, it's approaching from the negative x values. So it's going to be limit x approaches 0 minus sine x by x and limit x approaches 0 plus sine x by x. So this first one over here means that it is approaching from the left, and this one over here means that it is approaching from the right. So that's the limit notation. Now, the condition for a limit to exist will be when the left limit is equal to the right limit. So in the specific scenario of sine x by x, what we see is that as x approaches 0 from the right hand side, and as x approaches x approaches 0 from the left hand side, we get an exact same value. And therefore, we can say that the limit exists. What does that mean? If you see over here, I can't zoom in more, but essentially over here, or actually, let me open the calculator here. So yeah, so I have sine of x by x. And if I zoom in more and more and more, we see that the limit over here, as x approaches 0 from the right hand side, it is approaching 1. And as x approaches 0 from the left hand side, it is also approaching 1. And I can zoom in more and more and more to get even smaller x values. Over here, I have 0.00109, and that is very, very close to 1. Same thing from the left hand side, it is very close to 1. So essentially, what I can say is that if sine x by x, for this to have a limit at x equal to 0, what I should say is that since limit x approaches 0 minus of sine x by x is equal to limit x approaches 0 plus of sine x by x, I can conclude that a limit exists for this, and this is equal to 1. That is why the graph over here shows it approaching 1, even though the graph actually can never equal 1. So there's a transparent circle over there, which implies that it never equals 1. But because there exists a limit over here, which is equal to 1, the graph shows it to be included in the curve. Now, what are the additions, subtractions, and everything using limit? So I'm just going to use f of x and g of x as the functions. And if they have something like limit x approaches infinity of f of x plus g of x, I should write plus or minus. I can just write this as limit x approaches infinity of f of x and limit x approaches infinity of g of x. So essentially, we can separate them. Next, we have something multiplying it with a constant. So if I have a times this, I can write that as a and a over here. So that's another way. That's the second operation that you can use with limits. Now, how do we solve questions with limits? Let's take this for an example. Limit of x approaching to 0 of x squared minus 9 divided by x plus 3. So if you know your algebra, you can probably say that x squared minus 9 is nothing but the difference of squares. So you can write that as x plus 3 into x minus 3 divided by x plus 3. The x plus 3 will cancel out to give us x minus 3. Now all we have to do is take the 0, put that in x, and you'll get equal to minus 3. In this specific case, it is the answer that as limit as x approaches 0, x squared minus 9 by x plus 3 will approach minus 3. And you can check that on the graph over here. So I'll put x squared minus 9 divided by x plus 3. And if I zoom out, this is the graph. And it's a linear function because it simplified that over here. And it will be 0 is at 3, minus 3, which is what I got over here. However, the idea is that this one has another criteria over here that x is never equal to minus 3. If x was equal to minus 3 plus 3 will give us 0, and 0 in the denominator means that it's a vertical asymptote. So essentially what I'm saying is that if it is approaching any value other than minus 3, we can use that as a method. However, if it is approaching minus 3, then we have to use a different method. And what's that different method? Well, we can make a table over here. Let x squared minus 9 by x plus 3 equal f of x. So what I'm going to do is take some values which are less than minus 3 and take some values which are greater than minus 3. And basically, I'm going to make it smaller and smaller and smaller so that it is basically approaching, or it's very, very close to minus 3. So I can take something like minus 2.9999, and I can take something like minus 3.0001. And if I take those values and put them in this specific function, I should get some values. Okay, so I have my calculator over here, and I'll be putting those values, which is minus 2.999 and minus 2.001, in this function f of x. So let's write minus 2.999. That's the answer now. So I'm just going to use the answer function over here. So answer squared minus 9 divided by answer plus 3. And I know I missed that square over here, so I'll just put that there. What do I see over here? Minus 5.999. Now, over here on top, I'm going to do the exact same thing, but with minus 3.0001, minus 6.001. So, essentially, it is nearing minus 6. So, as x approaches minus 3, so I'll write this right. This is going to be approaching from the right hand side. So this is limit x approaches minus 3 from the positive side, because it's the right hand side of f of x, and this is equal to some value, and this is the other side, limit x approaches minus 3 from the negative side, sorry, of f of x. And these values will be very, very close to minus 6. So essentially what I'm saying is in this specific scenario, you can cancel these out to give us x minus 3 in the final result, and then you can just put x equal to 0 in that. However, if you were using a different, there's another equation, another expression, and you could cancel them out, but but you couldn't cancel them out, and there's a criteria given to you like this, then you would have to use this technique, which I will further develop in the next few examples. Now, another thing I can show is that as x approaches minus 3, which will be over here, minus 1, minus 2, minus 3, minus 4. Minus 3 is at 6, minus 6. So this, in fact, does work. Next, I have this question over here. Limit of x approaches to 0, tan x by x plus x squared. Now, there are two ways to solve these type of questions. We can just graph it, which is the easiest way to do this. So I'm going to write over here, sorry, tan of x divided by, it says x plus x squared, x plus x squared. So this is the graph over here. Now, what value is it approaching? It's approaching x equal to 0 from left hand side and right hand side. So as x approaches 0, we see that it is at 1, right? Now, that's the graphical approach, which is very, very easy. And you can do this on your graphic calculator as well, or on another app like Desmos, GeoGebra, anything. But if you were to do this manually, you would have to use really, really small values, which would be something like 0.001 and minus 0.001, and seeing how that fares and how the values near up, right? So let's make a table over here. Let this over here be f of x, because I'm not going to write tan x by x plus x squared all the whole time. Now, what I'm going to write is over here, the first one is x equal to 1 and x equal to minus 1. And I want to see what happens to this f of x at these two values. So I'm going to use my GDC over here. This is tan of, what is it, minus 1, yeah? So I'm going to write tan of 1, then divide that by 1 plus 1, because 1 squared is 1. So I'll get 0.779. So 0.779. Next, when it is minus 1. So tan of minus 1 is this, and I have to divide that by minus 1 plus 1. So minus 1 plus 1 is going to be an error because that is equal to 0. So this will not work. Let's make it a bit smaller. So I'm just going to write error. Make a gap over here, make that smaller now. Let's write x equal to 0.5 and x equal to minus 0.5. What is tan of 0.5? Just delete this line over here. So tan of 0.5 is 0.54, whatever. Divide that by 0.5 plus 0.5 squared. I do that, I get 0.73. Now, if I put minus 0.5 over there, this will be minus 0.75, 0.5, and then plus that squared will just be the same thing. So this is going to be 2.19. Now I'm going to make a big jump, okay? I'm going to make a big jump to x equal to 0.001 and x equal to minus 0.001. So tan of 0.0001, and this is going to be 0.0001 plus 0.0001 squared. This is going to be 0.49, 0.9999. Same thing with minus 0.1, 0.001. So I'm going to put minus over here, and then minus over here, and then minus over here. This is what? 1.0000. So what do we see over here? As x reaches very, very, very small values, um, very close to zero from either side, we see that we see that f of x tends to or approaches 1. So therefore, this limit is equal to 1. All right. Next is a lot more complicated, and so I'll be introducing another specific tool that I'll be using. So first, let's graph it over here. So it is 1 minus x squared plus 2x squared, 2x squared, 2x squared, ln, just put natural log over here, which is this x. So that's the numerator. And I will now divide this whole thing with, okay, I'll just remember that 1 minus sin pi x by 2. Okay, got it. Divide by 1 minus, go to trigonometry, sine pi x by 2. So there we go, that's the function. And this is as x approaches 1. So as x approaches 1, right over here, we get a value over here. How do I find a better approximation of that intersection? I can just use x equal to 1 over here, get that line, and where they intersect. This is approximately 1.62. Instead of using that tabular method, I'm going to be using SymPy on Python for this. So I already have it set up over here, and I'm just going to input this over here, and then limit approaches 1. So this will be 1 minus x to the power 2 plus 2x squared, put that in brackets, because why not, multiplied with simp dot log of x. So this is the numerator, and I can just run it over here to see if it runs accurately. So this is 2 into x, sorry. So I get this 1 minus x squared plus 2x squared log x, and this log is basically log base e, so that works. And then I divide that by 1 minus simp dot sine of simp dot pi into x into 0.5 or 1 by 2, same thing. And I close it, and there you go. I have the expression over here. Now all I need to do is just go over here and add another limit, simp dot limit, and then I write x approaches 1. So I get 16 by pi squared. Okay, now instead of x equal to that, I'm just going to write y is equal to 16 divided by pi squared. If I do that, you see over here, there's a perfect intersection of all three lines. That is the value that y approaches, or the function, this function over here, 1 minus x squared plus 2x squared and ln x by 1 minus sine pi x by 2 approaches 16 by pi squared as x approaches 1.